Our next talk is from our sponsor, Shopify, and it's titled Fun Passing Blocks Around. Please welcome Alan Wu from Shopify.
Hi, my name is Alan. I am a member of the Ruby core team and I work on improving the Ruby runtime at Shopify. I want to share some fun facts about the implementation details for passing blocks around in C Ruby today. Let's get started. So in Ruby, all methods implicitly take blocks, and methods can invoke the block they receive with the yield keyword. This is the most basic way to work with blocks. It works well, but has some limitations. For example, the method can't pass the block it receives to another method. It also can't save the block into a variable for later. For more flexibility, we can give a name to the block argument in our method. Yield still works, but it's also possible to call the block using the block argument. The block argument is a proc object instance, or nil, in case the method receives no block. Now, let's say you want to change the method to check whether a block was given, like this. If you want to be efficient with CPU time, this is where things start to get interesting. Let's call our method a couple million times to see if we can measure how long our script takes to run before and after adding the if check. On my computer, the version with the if takes about 3 times longer to run. Of course, the if check itself takes some time to execute, but it shouldn't make the script take 3 times longer. So what's going on? To spoil the surprise, the version with the if check allocates a proc object every time it runs. So this is my first fun fact. Some forms of block parameter usage don't allocate objects. The version without the if check is benefiting from a special optimization in the runtime. I will try to explain how the optimization works. But first, I want to go into why the optimization cannot be performed in all situations. Normally, local variables are reserved out of a single chunk of memory. It's done this way because the reservation itself can be done very efficiently. Reserving and releasing space pretty much involves adding and subtracting to and from a single number. We reserve space when entering a method and release space when returning from the method. This strategy runs into trouble when local variables need to stay accessible after the method returns. Let's look at an example. Here, we save the proc object for a block into an instance variable for later. We then return and call into method 3, which reuses the space method 1 used. When we call into the block that was saved, it would be wrong for the block to set the x that's defined in 3. So where is the local variable x defined in 1 if not in the chunk of memory for local variables? C Ruby deals with this problem by dynamically allocating heap space and moving locals there when creating the proc object for the block. In this example, the proc object is allocated at the highlighted line. When 2 returns to 1, 1 refers to freshly allocated heap space for the local variable x. This evacuation of local variables to the heap also happens when the Ruby program calls the binding method, but I digress. I've put more details about this operation on the screen in case you are interested. That was the second fun fact I wanted to share today. Local variables move when a proc object is created for a block. Okay, so let's talk about the special optimization that avoids allocating the proc object and hence avoids evacuating locals. We have seen that it's problematic to refer to the chunk of memory for local variables once the method housing the block returns. But it is fine to do it while the method is still running. So, if we can guarantee that the method housing the block is running, we can call into the block without evacuating the locals. The runtime looks for this condition by strictly limiting the optimization to 2 operations on the block parameter, passing the block parameter to another method, and calling the block parameter. Performing any other operations with the block parameter defeats the optimization. While the method receiving the block is running, we also know that the method passing the block is running. After all, the method receiving the block must have received it from somebody. C Ruby is very conservative when looking for these two operations. For example, assigning the block parameter to a local variable defeats the optimization. And as we saw, using the block parameter in an if condition also defeats the optimization. C Ruby's Ruby virtual machine uses a special instruction getBlockParam proxy to implement this optimization. You can search for it in compile.c to see how it targets this optimization. The instruction pushes a one-of-a-kind special object that stands in for the proc object. This special proxy object has a special call method that behaves similarly to the yield keyword when called. I've been talking a lot about this optimization, and I would be remiss to not give credit to its author. This optimization was written by Koichi Sasada-san, or KO1 on GitHub. So that was my third fun fact. C Ruby implements this allocation avoidance scheme with a special proxy object. Alright, I have one last thing to talk about. You might be curious as to whether this optimization is fully semantics preserving. If it is, then all possible Ruby programs should behave the same before and after the introduction of the optimization. This is important for keeping compatibility with the existing Ruby programs. Turns out the optimization did bring about a behavior change, particularly to do with the lambda method. To quickly summarize the issue, it turned out that the lambda method needs the special ability to tell the difference between a literal block and when passed in with the %, syntax. There is no straightforward way in Ruby code to know whether a block is a literal block, so I think it's easy to see how this very specific corner case was missed while introducing this optimization. The lambda issue was fixed in the 2.7 release, so this optimization is fully semantics preserving now, right? The answer is a definite maybe. There's an even more obscure and less important situation where the optimization poses a problem. It's so obscure and unimportant that I'm going to leave it here as a riddle for those interested to solve. That's my fourth and final fun fact. The lambda method has the special ability to tell whether the block passed to it is a literal block or not. Alright, that's all I have. Thank you for your attention, and I hope you have a nice day.
Thank you, Alan. We sure do have a nice day today. Thank you for the 3 and +1 extra fun facts. Alan Wu from Shopify.